I've recently done a set of videos talking about MicrROS bringing robot operating system to the Raspberry Pi Pico. So far they've demonstrated concepts, integrated key capabilities for me like FreeRTOS, and run against a simple virtual robot. In this video I'm going to use the techniques I have been learning and explaining to create a control system for a really simple robot. My video turntable is a simple robot with a single joint that can rotate clockwise and anti-clockwise, along with different speeds and stopping at repeatable positions. The idea is to use this for video recording work on my projects. This video pulls together concepts I've touched on in many other videos over the last few months. I will link them in the description. So this video is a great jumping off point for videos on stepper motors, Hall effect sensors, MicrROS and other concepts. In a previous video, I talked about a video turntable, the ability to rotate PCBs, small components, breadboards, etc. and see them from slightly different angles, because that's actually quite useful for getting clarity across what's going on and seeing them a little bit more in 3 dimensions. And also, let's be honest, still photos are quite boring, so giving something that actually moves is quite nice. The video turntable is a really simple robot. It has a single joint that can rotate by 360 degrees. You've probably seen in a previous video that I've modelled this in URDF for the ROS2 ecosystem. And we can use that visualization to explore what's going on. ROS2 uses the joint state message in order to actually animate the robot within our viz. And so we've got our Pico publishing that joint state to simulate the turning of our turntable. I wanted then to be able to command the robot from ROS2, to be able to command it to rotate continuously using the command velocity topic, or alternatively to move to a specific position for a time in the future. So, within 5 seconds, please get to the position of 90 degrees round. And I used a do pose message to do that. My video turntable, of course, also responded to local switches and rotary encoders and allowed you to see its position via the OLED screen. All of that functionality I want to keep. I just want to add this ROS2 control system on top. In this video, I'm extending the Pico's firmware to support MicrROS, so we can command the turntable from the ROS2 via the MicrROS agent running on a Raspberry Pi. RViz I'm going to run separately on my VM to also visualize, just to make sure that actually what I'm seeing my robot do in real life is what the model is doing, and therefore everything nicely ties up. It's a good experiment. My thanks go to PCBWay for sponsoring this video and helping me out with the manufacturer for the PCB for this project. PCBWay are a great partner with the capability to do PCB fabrication and soldering of boards if required. They also do 3D printing, CNC, sheet metal fabrication and injection moulding. A great partner for any robot project. So this project is going to be an upgrade of the software control system rather than the hardware. I'll put a link to the video talking about the hardware in the description. But let's just have a quick recap on what the hardware did and how that worked. So the turntable is simply a spur cog driven table. And I'm driving it from a 28 BYJ 48 stepper motor. They're really cheap stepper motors, easy to get hold of. And using a ULN 2003 Darlington array to drive it. I did a whole video talking about stepper motors previously, which you can go and have a look at. I'm going to need to, of course, detect the 0 position on the turntable. In some other projects, I've done that using an optical slot detector. On this project, I chose to use a A3144 Hall sensor. So this is a detector of the Hall effect, which is detecting magnetic fields really. So we're going to put a magnet onto the bottom of the turntable. That's really easy to fix and stick on with a bit of glue. Much easier than actually building a slot detector bit of hardware. And I, of course, have got a whole video talking about the A3144, and I'll put a link to that also in the description. On board, I've got some switches and rotary encoders for starting and stopping the turntable and setting its position and speed, etc. I've also got control of WS2812B LEDs, which I was using for lighting. I don't have a YouTube video talking about those, but they are included within my micro projects course on Udemy on the Pico. So if you're interested and want to know more about how to control those sorts of simple devices, go have a look at that course. I'll put a link in the description, of course. The architecture of this project is just an aggregation of the previous turntable project and the MicrROS pub sub example I've been working on. The stepper motor becomes our pub sub entities. It has the active loop managing the stepper motor, so it can publish the joint position of the stepper motor. The UI for the turntable project remains intact and is able to also command the stepper motor. In the previous MicrROS and FreeRTOS projects, I had the MicrROS bridge and a pub sub task. The MicrROS bridge remains intact in this project, and the stepper motor agent takes over to handle the publish and the subscribe. So this can publish the joint state each time the turntable moves. Joint state is basically a set of arrays providing the state of the joint. We only have the one joint to publish, post to table, and we also only going to publish the position of that joint in radians. Actually, the stepper motor loop publishes a bit too quickly, so the queue into MicrROS bridge is actually full all the time. When the queue is full and we issue a publish, actually the code's just going to ignore that. For this robot, when I'm using this just to visualize in RViz what's going on, that's fine. Keys not to publish anything else, otherwise we'd start having some serious contention problems. For future robots, I will need to be a bit more careful in how this queue fills up with publication requests. We also receive command velocity messages to continuously turn the turntable. Command velocity is a twist message. This is basically speed. The robot is moving in linear, X, Y, and Z, and rotation in angular speeds. Our turntable can't move along the linear axes. It can just rotate around the Z axis. Therefore, I just use angular Z. This is radians per second. It can also receive a do pose message, requesting the turntable to move to a specific angle by a time in the future. Pose stamp basically describes the position of the turntable at a point in time. I use the header to give me a future position, then the orientation of the z-axis encoded as quaternion. Of course, we can still command the stepper motor from the local UI, and there is an active task managing this and displaying the position of the turntable. The rotary encoder also uses tasks for sampling its position. I've put all of the code for the project on GitHub. A link to the repo is in the description. This contains the ROS2 workspace with the URDF model of the turntable, and indeed the RViz settings and the Python launch script to launch those up. The firmware for the Pico is also there in terms of all of the source code to build that, and that includes the bridge over into the MicrROS agent world, and that's going to be over USB. The hardware and circuit and indeed 3D models for printing the turntable project are not within this repo. I've continued to use the Mark 1 version, so please look into the Mark 1 project repo. Firmware for our video turntable will be on our Raspberry Pico, and then that's connected via USB to a Raspberry Pi, which is running the MicrROS agent and the ROS2 ecosystem. I'm then using a VM to run a copy of RViz as well, so I can just show some visualizations. I've got a launch script that I'm running up in order to load up RViz and the URDF of the turntable as a robot, so that we've got that description and we can just visualize to compare that and the robot itself, or the video turntable itself, are doing the same things. So we use the topic pub command to send a twist message to tell the turntable to rotate clockwise, and then counterclockwise with a negative Z rotation. Then I'm going to use a Python script to send post-stamped messages to the turntable. Each one is a request to move 90 degrees further forward or backwards within the next 5 seconds. And then it's going to stop for 5 seconds and then it's going to do the same thing again. So we can follow both the turntable itself and the RViz visualization of what the turntable is doing. So that is the Mark II of my video turntable. In the future I want to add a robot control camera to the rig. Thank you very much for watching. Please do like the video as it helps other people find it. Please subscribe and hit that notification button for more videos from me. Goodbye for now.